Some folks get confused between centripetal and centrifugal forces, and reasonably so. Let me illustrate with an example. So let's say you're looking down on like a circular racetrack, or it doesn't have to be a full circle. It could just be a fraction of a circular path. So let's erase a little bit here. And maybe there's a straight segment of road that takes a circular bend. So maybe the road points a little bit northeast, and then from there rounds a curve and continues on to the west. Okay, now picture yourself entering this curve. Maybe you're in the back seat of a vehicle whose velocity initially is pointing tangent to the curvature. Call that V subscript T for V tangential. And we zoom in, and this is you kind of smashed up against the side of the car here. So the car, of course, is going to change direction. In a moment, its velocity vector is going to point this way, and as it continues around the curve, then the velocity vector points this way. And because it's always changing direction, that's a way of changing velocity. And even though its speed might remain constant, because of the change in direction, this can only occur if there's a centripetal force to push the car toward the center of the circle. Now you probably realize what that force is. The road grips the tires and pushes the car, thanks to the force of friction, toward the center at all times. So you notice the angle between the tangential velocity at any instant and the angle and the direction of the force of friction always forms a 90-degree angle, and that force is constantly toward the center. So that is indeed a centripetal kind of force. However, you might think that the tendency of your body is to fly outward. After all, why are you getting smashed up against the inside of the car? So here's an idea. What does the law of inertia say about all this? Your body has a tendency to continue moving in a straight line. So, oh, how unfortunate would this be? If the door suddenly flew open, then what would happen to you? Some people say you would fly outward, but you wouldn't. There'd be no desire to move in this direction. If anything, you'd fly tangentially. Now, it's true, if your body continues to move on this path tangent to the curvature, then at some point in time you will be farther from the center than you were originally. But it's definitely not due to some sort of force that pushes the outside, and it's not due to any force at all. The reason you might continue to move in a tangential path is due to the law of inertia. And inertia is not a force. Inertia is a property given to you by nature of having mass. In any case, ideally, the door does not fly open as you drive around a curve, and therefore, what's really going on, as you sit here in the back seat with the side of the car, the door of the car pushing on you, it's pushing inward on you. So friction provides the centripetal force to make the car go in a circle, and the contact with the door itself provides the centripetal force to make you go in a circle. So anytime something moves in a circle, it's indeed due to a centripetal force and never centrifugal. Anyhow, now that we've cleared up, in case you might have been carrying this misconception, let's put into practice this idea about centripetal acceleration. We've already found that there's an equation that helps us calculate the value of centripetal acceleration. If we take the tangential velocity squared and divide it by r, or I suppose what I really mean here is the tangential speed squared, right? Since we're just looking for the magnitudes. Some cars will skid out. Now, I don't really like that term because just like I stated, there's nothing pushing the car outward. If you exceed what friction is capable of providing, then there will no longer be enough centripetal force to ensure that the car rounds the curve. And if you've ever gone too fast around a curve yourself, especially if you've driven on icy or snow-covered roads, then you know exactly what can happen. The law of inertia takes over, and instead of rounding the curve, the car continues forward due to the law of inertia. So yes, like I said, that ends up moving it on a path that leads it farther away from the center than it would have been if it rounded the curve, but it's certainly not getting pushed outward. If anything, I don't know, I guess the word would be, instead of skid out, would be skid tangentially. In any case, that's just a matter of semantics. So the car might lose the benefit of the force of friction, so to speak, when rounding a curve if it accelerates centripetally at more than 1.25 Gs. In that case, what would be the maximum safe speed for a car that goes on a circular racetrack whose diameter is 180 meters? Okay, so let's label this and say R equals 90 meters. If the diameter is 180, the radius is 90. And then this maximum value for the speed is the quantity we're trying to solve for, and we're given that the maximum centripetal acceleration would be equal to 1.25 multiplied by 9.8 meters per second squared, right? 1.25 Gs. So 9.8 times 1.25, well, that's 12.25 meters per second squared. Okay, so we just have to rearrange this equation. So if we multiply both sides of the equation by r and then take the square root of both sides of the equation, we find that the speed would be equal to the square root of the product of the centripetal acceleration and the radius of curvature. So in this case, it would be equal to the square root of 12.25 meters per second squared multiplied by 90 meters. Now take a look at the units. Meters times meters gives us meters squared. We still have per second squared, but in the end we're taking the square root. So this looks correct. Grab a calculator, play along at home. 90 multiplied by 12.25 is a little over 1,100. We take the square root of that result, and we get that the maximum safe speed would be equal to about 33.2 meters per second. Any faster, and there's just not enough centripetal force by virtue of friction to maintain the curve path. But any slower, and the driver would be able to negotiate the curve. Okay, here's another problem with an object driving around on a circular track. All right, this time we're told that there's a acceleration that takes place due to a change in speed. So let's picture, there, that's our car. A race car uniformly accelerates from rest, so the initial speed is equal to 0, and it finally reaches a speed of 40 meters per second. The driver travels 125 meters along the track during this period. We're not given the radius of the track, we're asked for that. So it's hard to picture exactly how far around, so I don't know. I'm just going to guess and say perhaps the car is driven this far by the time it's gone up to a speed of 40 meters per second and covered 125 meters. Okay, so we'll see. There's no guarantee I've got the scaling of this correct. So the radius of curvature is a question. When it does reach this point, the speed has changed from 0 up to 40 meters per second, and the arc length is 125 meters in that case. Oh, and let's see. A race car drives along a track, uniformly accelerates, reaches a speed of 40, covers this distance. Oh, and the acceleration was uniform. Okay. Well, we should say the tangential component to that acceleration was uniform, but the overall acceleration was not uniform because it includes both a centripetal and a tangential component. So let's be careful, and every time we solve problems, we have to make some assumptions that might not be clearly stated in the problem. It's the tangential component to the acceleration that's uniform, but the total acceleration, which includes a tangential component and a centripetal component, is not necessarily uniform. Well, we can do some kinematics here. We don't know what that tangential acceleration is equal to. However, we know the initial velocity is 0, and the displacement, no wait, not delta x, not delta y. Let's see, well, best we can do is call it delta s, is 125 meters, and the final speed is equal to 40 meters per second. Okay, so sure, we should be able to solve for both the what that value of tangential acceleration is equal to, as well as how much time that process took. So let's solve for both of those. Even though we're not asked for that amount of time, it might help inform us. So yeah, let's find the acceleration first. Final speed squared equals initial speed squared plus 2 times acceleration times displacement. Initial speed is 0, so the acceleration is the final speed squared divided by double the displacement value. So this is 40 meters per second quantity squared divided by 2 times 125 meters. Grab a calculator. 40 squared divided by 250 gives us a value of 6.4 meters per second squared. Okay, now as far as time is concerned, final velocity equals initial velocity plus acceleration times time. So the time that it took for this process would be a final speed of 40 meters per second divided by an acceleration of 6.4 meters per second squared. And that comes out to a time of 6.25 seconds. So let's see where this problem continues to take us. Okay, exactly 5 seconds after the car starts to move, the centripetal acceleration has the same magnitude as the tangential acceleration. What's the radius of the track? What are they trying to say here? This is one of these read the problem a second time situations. Let's see, exactly 5 seconds. Why 5 seconds? I thought the answer was 6.2. Well, it took 6.25 seconds to make it this far. So I guess now what the problem is saying, well, let's not consider that full amount. Maybe up to here, what's going on? So this whole thing took 6.25 seconds, but up to here only takes 5 seconds. So what would be going on at that point in time? We're told at that moment, the tangential acceleration, which points this way, and the centripetal acceleration that points this way are equal in magnitude. And by the way, the centripetal acceleration is always calculated as v squared over r. So I guess the question is, what is the tangential speed when the car gets to this point? It's not going to be 40 meters per second because it only has the benefit of 5 seconds of increasing speed as opposed to the full 6.25. Oh, so in fact, that shouldn't be hard to calculate. Again, we could use this equation, but let's just say that we're only going to use a time of 5 seconds instead of 6.25. So final velocity is initial velocity plus tangential acceleration multiplied by time. So the final tangential velocity is equal to 0 plus 6.4 meters per second squared times 5 seconds, which gives us 32 meters per second. Right, not quite the full 40 meters per second it would have achieved after 6.25 seconds. Okay, so if the car has reached a speed of 32 meters per second when it gets here, then we can use this formula to find out what the centripetal acceleration is. So this would give us 32 meters per second squared divided by, oh, no, wait a minute, we don't know r. Oh, but we know what the centripetal acceleration is. The problem says, if we read carefully once again, the centripetal acceleration has the same magnitude as the tangential acceleration. Well, the tangential acceleration, we made this assumption, was always the same value, which is 6.4 meters per second squared. The centripetal, that's the tangential acceleration. The centripetal acceleration is always changing. At first, because there's no speed, at the very instant it begins, the centripetal acceleration is 0. And then as its velocity vector starts to get longer and longer, the centripetal acceleration gets bigger, and the car gets here, and now the centripetal acceleration is bigger yet, and now it gets here, and it's even bigger, and so on. Ultimately, it reaches this moment in time where the centripetal and tangential accelerations have the same value. So what we're really dealing with is a case where the centripetal acceleration is just as great as the tangential acceleration at this one particular instant in time at t equals 5 seconds. So that means they're both equal to 6.4 meters per second squared. And at that given instant, the tangential velocity is 32 meters per second, so we're trying to find the value of r. So if centripetal acceleration is v squared over r, then a little cross multiplying tells us that r equals v squared over the acceleration, which would be 32 meters per second squared divided by 6.4 meters per second squared. So the units are meters squared over seconds squared over meters per second squared. Second squareds all cancel, meter, meter, we're left with meters, hallelujah, we're trying to solve for a radius. So if we grab our calculators, take 32 squared and divide it by 6.4, we get a value of 160 meters. So there we have it. We've answered the ultimate question here, what is the radius of the circular track? And notice how important it was for us to, at the very least, draw a diagram and start to do some labeling in an attempt to solve the problem, as opposed to just jumping straight in and grasping for equations. So conceptualizing the problem is always the key, and hopefully with enough process and conceptualization, you can end up with the correct result. Hey, thanks for watching.